Hello, this is Dr. Christy Lukes, and we are going to continue our discussion of error analysis by looking at propagation of error. So the idea here is we have measured values with some error estimates, and now that we're going to use those in calculations, how much error is in our calculated values. So we're going to be looking at calculation of strain. Okay, that's nice. It's a ratio of the length under some sort of tensile force to the unstressed sample length. So it's a dimensionless quantity here. Let's say that we have L naught measured to 11.9 plus or minus 0.3, and L is 10.2, so this is under compression, plus or minus 0.5. All right, so those are our two estimates. Now, if we wanted to know what the estimate is of lambda, well, we would take 10.2 over 11.9. But what is the error on that? That's the question for today. So one thing we can do is we could just try doing it by brute force. So let's take all those minimum values and all the maximum values and put them together in all the ways we can think of and come up with what the answer is. So the actual is 10.2 over 11.9, which is 0.86. If I took the smallest numerator with the largest denominator, that would give me the minimum value, which is 0.80. And the maximum would be taking the largest numerator and the smallest denominator, so 0.92. Okay, so that says that my answer is going to be 0.86 plus or minus 0.06. Okay, but that's going to be an overestimate. Okay, so we really don't want to do that. That's going to overstate the amount of error. All right, it's a brute force approach, and something as simple as this, it's not too hard to do, but it also overestimates our error. So what we want to do is we want something that's going to be more realistic of the error. And so we're going to go to calculus to do this. Now, if we consider lambda to be a function of these two variables, L and L naught, then we can look at the error of this by using how the value lambda changes with L times the error in L, square that, how the lambda changes with L naught times the error in L naught, square that. The sum of those, square root of that, is going to be an estimate of the uncertainty in the calculated value lambda, the strain. Okay, so each error here, so the subscript is telling me what it is, what variable I'm looking at the error for. And so I could go through and do this. And all I need to know is what is the function for lambda as a function of L and L naught. Now in this case, it's just L over L naught. So these calculations are not too difficult. D lambda dL naught is negative L over L naught squared. D lambda dL is 1 over L naught. Plugging numbers in, I get negative 0.072 and 0.084. Now this one gets multiplied by the error in L naught, which we said was 0.3. This one is going to get multiplied by the error in L, so 0.5. We'll square each of those, square root the sum, and we end up with 0.047, so my error would be 0.05. All right, instead of the 0.06 that we got by the brute force overestimate method. So this propagation of error is the way that we want to approach this. And if you have more variables, you're just going to continue this pattern, squaring and adding together all the various terms you have. So let's look, well, okay, first let's talk about this. So 0.86 plus or minus 0.05 is the correct value. We would have come up with 0.06, but that's a 20% overestimate, okay? And propagation of error is the way that is considered to be the accurate method of error analysis, okay? Now, one thing that's nice to know is that you can break a very complex function up and like find the error in, maybe there's an exponential that has an unfortunately challenging expression, like Arrhenius's law, something like that. You can find the error in that exponential term, okay, and then use that in your calculations for the future and do it piecemeal. And that can make your math a lot easier, okay? So let's look at looking at heat loss, okay? So mass flow rate times C sub P times the delta T for the fluid. We're just looking at one fluid. And I've got a flow rate of 10 pounds per hour plus or minus 0.2, 150.4 plus or minus 0.1, and 123.2 plus or minus 0.1 are my delta T for my fluid. And C sub P we will consider in this case to be constant, that we know that value, okay? Now, if you are not sure, if you have different values of C sub P for these two temperatures, you actually will have an error on this known physical quantity also. So, okay, if you do that and you get 1.034 plus or minus 0.002, going from the maximum to the minimum, this is a very small quantity, right? It's in the 4th decimal place compared to our other measurements. So as we'll see, is frequently these things can be treated as constant. But let's carry through saying that we recognize that there's a temperature difference here. So the error is going to be the derivative of Q with respect to each of the variables times the error in that variable. So flow rate, the inlet temperature, the exit temperature, and that C sub P. So I'm going to do all of those derivatives. So here it is with respect to M, it's C sub P times delta T. With respect to TH, it's flow rate times C sub P, negative flow rate times C sub P for the outlet, and M dot times delta T for the C sub P. Plug the numbers in with my error estimates, and what you'll see is we end up with 5.625 squared for the mass flow rate term, 1.034 squared for the TH, same for the T out, and C sub P 0.544 squared. Add those together, square root, I get 5.84. Okay, only get one digit on error, so that means 6. So our Q, calculate the Q, 281 plus or minus 6 BTUs per hour. Now, the other thing about doing this, though, is that I get a lot of extra information. So what I see is that the piece of this that caused the most error was the mass flow rate. Had I been able to measure that more precisely, I could have reduced my overall error. The C sub P, that contributed the least to the error analysis. So had I called it constant, it would have probably been just fine. Okay? So, as you're doing these propagation of error calculations, be sure that you are indeed taking the time to look at it term by term. Okay? And I think that that is the end of this example and the end of our propagation of error. Now you will need to use propagation of error on all lab reports to figure out what the error is on your final results. Thank you very much.